The fourth part of the lecture is about isotropic and anisotropic material. Isotropic material. In the case of uniaxial test and Young's modulus. In a uniaxial test, sigma 11 to be constant and sigma ij to be 0. For example, here you see from the original shape, it's elongated, except that it's elongated along x3 axis, so sigma 33 is not 0 here. Also note the change in the cross section due to the Poisson ratio. Okay, from the relation, sigma ij is equal to lambda delta ij epsilon kk plus 2 mu epsilon ij. We get, if setting sigma ij to 0 and keeping sigma 11, we get these three relations. Okay, keep them in mind. Now solving 2 and 3 for epsilon 22 plus epsilon 33 based on epsilon 11, and substituting it in the first one, we can find this relation. Sigma 11 is equal to E multiplied by sigma by epsilon 11. And we find E based on mu and lambda this way. For the Poisson ratio, nu, that relates lateral deformation, as you see here, we can use equation 2 and 3 divided by epsilon 11, and as a result we get nu equal to minus epsilon 22 divided by epsilon 11, or minus epsilon 33 divided by epsilon 11, which is equal to lambda over 2 mu plus lambda. Now, in the case of pure shear and shear modulus, we assume sigma 12 is equal to sigma 21, and they're constant, and sigma ii's are 0. Have a look here. It's the case of pure shear. So we get only sigma 31 and sigma 32 without any sigma 33. So just know that, and here we're working on the plane normal to x3, but it's not the case in the text. Okay. Again, using the equation relating sigma and epsilon, we get sigma 12 is equal to mu epsilon 12, and that's basically G. So G is equal to mu, and that's called shear modulus. Okay, now let's review some concepts. The following relation can be written. Mu is related to E, Young modulus, and nu, Poisson ratio. The same, E can be related to mu and lambda. G is mu, and lambda can be found based on nu and E, and also nu can be found based on lambda and mu. There's a full list in table 6.2-1 in the main reference book of the course. So as you see, E, Young modulus, nu, Poisson ratio, and G, shear modulus are not independent. We can define an additional constant here that we call bulk modulus K, which is defined here. K equal E divided by 3, 1 minus 2 nu. Also, we can write Hooke's law in terms of strain. And for the isotropic material, that's how it looks. Just pay attention to the symmetric part of C inverse tensor. The coefficient C inverse is called compliance. Okay, here's an example. It says given the following strain components at the point P within a material, and knowing the Young modulus and shear modulus, compute the corresponding components of the stress tensor sigma. So we already know that mu is equal to G. For E, based on mu and lambda, we have this relation, but you may recall that we don't have any relation for lambda based on E and G. So let's solve these two to find lambda based on mu and E. Lambda becomes equal to mu multiplied by 2 mu minus E divided by E minus 3 mu. Okay, now we have it. We already know that mu is equal to G, so it's 12 megapascal, and lambda can be found from this relation to be 12 megapascal. Okay, let's write the matrix form of Hooke's law. I calculate the C matrix. I've already calculated that. Just pay attention. This side of the matrix is basically an image of the other side. It's a symmetric matrix. We already know the strains, and I've already calculated that in MATLAB. The stress values becomes for sigma 1, 1, 2, 2, 3, 3, 1, 2, 2, 3, and 3, 1 becomes these values in this column vector. As I pointed out, don't forget that the symmetric part of the matrix, I just didn't repeat it, but here they are, so you know how it's filled. Okay, here's another example. It says let's consider an isotropic elastic material for a plate in a plane straight state, plane stress state. Determine the out-of-plane strain component E33 from the measurement of the in-plane normal strains E11 and E22. Okay, it's a plane stress. So we know that sigma 33 is 0. Let's use Hooke's law now for the strain as a function of a stress, and using the already mentioned relation, we can find epsilon 1 1 equal to sigma 1 1 minus nu multiplied by sigma 2 2 plus sigma 3 3. We already know that sigma 3 3 is 0, everything divided by E. So epsilon 2 2 becomes something similar as a function of sigma 2 2, and there's no sigma 3 3 as you see. Okay, solve for sigma 1 1 and sigma 2 2. We get sigma 1 1 equal to E over 1 minus nu square multiplied by epsilon 1 1 plus nu epsilon 2 2, the same for sigma 2 2. Okay, again, from Hooke's law, we calculated this time epsilon 3 3 based on sigmas, and we already know that sigma 3 3 is 0. So we already calculated sigma 1 1 and 2 2 based on epsilon 1 1 and 2 2. So just replacing that in this relation, we can find epsilon 3 3 based on epsilon 1 1 and epsilon 2 2. Basically, the out of plane strain based on the the in-plane normal strains. And here it is. The result is minus nu divided by 1 minus nu multiplied by epsilon 11 plus epsilon 22. Okay, anisotropic materials. We start with a biological example. Consider muscle fibers. So you know that the muscle as a whole is a bundle of a smaller strands of muscle fibers. The muscle fibers have properties such as they are parallel to an axis. Here we name that axis x1, and we have plane of isotropy, which is x2, x3 plane. And you see that we have rotational symmetry along around that fiber axis. So properties of such material are symmetry about an axis that is normal to the plane of isotropy, which is x2, x3 plane here, and 3 mutually orthogonal planes of reflection symmetry. So basically we can find 3 planes that the arrangement of the fibers are symmetric with respect to them, and we have axial symmetry with respect to x1, the fiber axis. So it doesn't matter how much you rotate a frame, the property of the material doesn't change. We call this material transverse isotropic material. Okay, let's see how we can handle these properties. We start with monoclinic materials. It has one symmetry plane. So we can reverse one axis without any change in the stress tensor. Let's drive the material law. Assuming the plane of symmetry is x1, x3, as you see in this figure, then x2 can be reversed. So in the reversed configuration, x2 prime becomes minus x2. Here's the corresponding coordinate transformation for that. As you see, x2 is reversed. If we employ alpha to transform the original frame x. So as a result, we can find the transformed stress tensor from R sigma R transpose, and it basically gives us these relations. Sigma 1, 1 prime is equal to sigma 1, 1, sigma 2, 2 prime is equal to sigma 2, 2, the same for sigma 3, 3. But you see that to get the stress tensor invariant, we should get set sigma 1, 2 prime equal to minus sigma 1, 2. The same for sigma 2, 3. You see the same thing for epsilon as well. Okay. We need some algebraic manipulation to find the rules that enforce these relations. I leave that to you to read that if you're interested. But at the end, we end up with only 13 independent coefficients. And the material law becomes a sigma equal to C for the monoclinic material multiplied by epsilon. Okay, note that we have sigma 1, 1, 2, 2, 3, 3, and the rest of elements are unique as well, but note that now some of the elements are 0. As a result, we have only 13 independent coefficients. Okay. Orthotropic material, it has multiple symmetry planes. You see 2 of the symmetry planes here, basically x1, x3, and x1, x2 planes. Okay, they have three mutually orthogonal planes of symmetry, so we can reverse one axis at a time without any change in the stress tensor. For example, x1 prime can be equal to minus x1, and the same can be done for x2 and x3. Okay, these are the transformation rules. Here x1 is reversed, here x2, here is x3. And following the same argument, we end up with only 9 independent coefficients. And the material law is as you see here. You notice that now we get more zeros and only 9 independent coefficients to deal with. Okay, then we get a transverse isotropic material, basically our muscle fiber bundle. They have three mutually orthogonal plane of symmetry, like orthotropic material, but we get axial symmetry with respect to an axis. Here is x1. So rotating the frame around x1 doesn't change the stress state. This part is similar to the orthotropic material, but we have to enforce the rotation around x1 axis as well. So apart from the transformation laws we saw before, we have this new one which enforces the rotation around x1 axis. Following the same argument, we end up with only 5 independent coefficients. And here they are. Note that we still have all of the zeros, but C44 is repeated. Also, we have C22 repeated for C33, and also we get C12 repeated. Also here we have C55 calculated based on C11 and C12. As a result, we have only 5 independent coefficients. Then we may have cubic materials. In cubic materials, we have 3 mutually orthogonal plane of symmetry, as we've seen in orthotropic material, plus 90-degree rotation symmetry with respect to those planes. So we get the planes of symmetry as we saw before, but we can rotate the frame 90 degrees between any of those symmetry planes, and still the material, the stress in the material doesn't change. So x1 prime equal to minus x1, we've seen that before, but now we can basically interchange the axis, for example, x1 with x2, or x1 with x3, or x2 with x3. So the orthotropic transformation laws and the axis interchange transformation law. Here x1 and x2 are interchanged, here x3 and x1 are interchanged, and here x2 and x3 are interchanged. Following similar argument, we end up with only 3 independent coefficients, and the material law is as you see here. Okay, you see that the half of the diagonal elements are C11, the other half of them are C44, and the only non-zero off diagonal elements we have is C12. So we get only 3 independent coefficients in that case. That's basically what we needed to know about an isotropic material with symmetry. So let's review the types here with some new figures that help you understand it in an alternative way. We have full anisotropic
material, there's no symmetry, 21 constant you get in the C tensor. You see that the cube, it has different length, different angles, and twisted, so it's not aligned with any of the planes. Then we have monoclinic. You get one symmetry planes, a 13 constant, and that symmetry plane in this case is XY plane. Then we have orthotropic. We get 3 symmetric planes, 9 constants, and you see that XY, XZ, and YZ are the symmetry planes. You may notice we have right angles now in the cube, but still the length of the cube edges are different, A, B, and C. These are a stress or a stiffness cubes. So another way of visualizing the concept. We have transversely isotropic material. We had 3 symmetric planes plus 1 axial symmetry. This is again our muscle fiber bundle. It gives us 5 constants. And finally, we have cubic material with symmetry planes and 90-degree rotational symmetry or axis interchangeability. It reduces C to only 3 constants. And you see now the all of the angles are right angles. All of the planes are aligned with the symmetry planes, and all of the lengths of the stiffness cube are equal. And finally, here is an activity example for you to try before attending the live session. It says for an isotropic material, demonstrate that nu is more than -1 and less than 0.5. Good luck.